W1VLF. All right, so we're out here at the test range. All my measurements when I do these tests are made from that window right there, which I open up to give me an unobstructed path of the range here. So let's walk up to it. I have two weak signal sources out here right now. One of them is much weaker than the other. This one just puts a constant carrier up, so it's something that's on all the time, and it's not nearly as weak as the other one, and that's this guy right here. This guy does Q65 for 30 seconds, CWID, and then carrier for the rest of the 60 seconds. And if you notice, there's a Wi-Fi antenna on the back because internally this box grabs its timing for Q65 from my network in the house. So if you look at these two, they are less than 3 feet apart. And it's very easy to distinguish each one of those and almost completely null it out. So if we look here, I don't know, that's maybe 8 feet by 8 feet, right? So that opening, and I'll show you this on the detector after. That opening is 8 feet by 8 feet. Let's call it that. It might be something different. Needs some work too. But there's the source, a 5mm LED. All right. So I just wanted to show you where this whole thing is started from, and then back at the house to the right of the air conditioner is the window that I'll be shooting through to do these tests. All right, so we're in the house here. The window is open. By the way, this window is 20 dB of attenuation at 940. Actually comes in really handy, but I have it open right now. There is the barn where the weak signal source is. And here's the receiver. This is a 10-inch by 10-inch Fresnel lens. Really hacked together, hot glue. I have some stuff to build a better looking receiver. And I guess I should be embarrassed to show people this stuff, but hey, it works. So, but here's the important thing. Okay, so this 10-inch by 10-inch grid is gathering information, all right, in terms of the 940 source that's out in the barn and a whole bunch of other crap which is unwanted. That's light. So let's take a look at this transimpedance amplifier, because this is a slightly different arrangement than what Fred and Renee and those guys are using. I'm using a discrete LED, photodiode, and this transimpedance amplifier. And here's a closer look at that. Okay. The output, wow, that's weird. Oh, okay. Something's going on in the camera here. This is the output. It's a N connect, SMA goes over to my little AirSpy receiver here. And the input is typically an SMA here, but I've taken the SMA off so that I can get a much shorter connection to the photodiode. Okay, and I'll try to show you this. I'm not sure you'll be able to see it really well. Maybe I'll snap some close-up pictures of this, but the detector sits inside this box, inside this little box. And the reason it sits in there is because it's 100% shielded. The only thing that come out are two leads. One to man, I don't know, I guess it must be something's going on with the camera here. Anyhow, let's look at it from the other side. One goes to ground, the photodiode. The other side of the photodiode, which is the hot side, is decoupled from this amplifier. Okay, now that's important because in sunlight, this makes probably a half a volt in bright sunlight of output level. So you're shoving a half a volt right into this amplifier that's really designed for looking at picoamps and milliamps of current. So that's a problem right off the bat. So to fix that problem, which made this work significantly better, I put a small coupling capacitor in there, okay? That blocks the DC from getting into that amplifier. Okay, that takes care of that problem because we don't really care about DC at this point. In fact, we don't want it. We're looking at a carrier at 14 kilohertz, which is 17 kilohertz, which is coming from the weak signal source. So what's the problem? Well, the problem is sunlight is so great that the amplitude of the sunlight falling on this detector here inside the box is literally taking that detector and forcing it into saturation. And it can no longer see the very weak signal. Can you imagine at 150 feet, a very weak signal source trying to compete with the sun? It's just not going to happen. Although, if you look here, I have some filtering, okay? That's a bandpass filter for 940 nanometers. So we've taken care of one of the problems, and that is we want to get rid of the DC that's coming through here. We've also filtered, so we're only looking at a very narrow spectrum, maybe 10 nanometers. But somehow that's still not working very well. And it's because the sun is forcing the photodetector into saturation. Okay, so here's a quick demonstration. If you look at that photodetector, I hope I'm far enough away so this is in focus. You can see the whole area is pretty brightly lit. Now if I cover up the lens, you can see how it goes into just the ambient amount of light that's scattered and falling onto the detector. But if I pull this away, so there's a ton of light there, all right? And a couple of things, let me hold the camera here. A couple of things are happening. If you look at this stick, I hope you can see that. I don't know if you can or not. But this stick shows a square in the middle of it, and that square is the opening of the barn. So my detector size is roughly the same size as that square. So what does that tell you? That tells you that there's a ton of light falling on the detector from that 8 foot by 8 foot opening. But the only thing we want from that 8 foot by 8 foot opening is that tiny little LED. So we have a lot of noise falling on the detector. And when I say noise, I mean sun. You know what? I better check and see if we can actually see this okay. Okay, I just reviewed the footage and it turns out you can't really see. So I'm going to try to flip this popsicle stick around. And now you see the little square in the middle. Very hard, still very hard to see. But that square is that 8 foot opening. And that 8 foot opening translates into the actual detector size behind this filter. Now the detector doesn't care where you put the light on it. It makes output power from that, okay? But the only thing we really want, again, is that tiny little LED. The rest of it is noise. Okay, guys. Now here we're doing a couple of pieces of testing. Now I want you to take a look at this. It says 44 dB signal to noise ratio, and there's our carrier. Okay, this is the weak signal source, and I'm pointing directly at it. Okay, so we have about a 44 dB signal to noise ratio now. And if you look, again, there's a whole bunch of light impinging on that diode, which we don't want. So let's take a look at the noise floor when I physically cover up, and I'll use a old t-shirt here, when we physically cover up the detector. Okay, so the signal drops, and so does the background noise. All right, now we're back again. And if you look, we have 42 dB signal to noise ratio. All right, and I'm going to apply some bias now. And here's where I applied the bias, right here on this wire. I'm going to put some bias on it. Okay, that's a very small voltage right now. And then I have a pot. It's a 100K pot across 1.5 volt battery. So what I'm going to do is, well, let's take a look at what the signal to noise here is. It's now 47. Didn't make a hell of a lot of difference. It made a little, but not a lot. So let's turn up the bias. All right, so I'm forcing that diode that's making roughly, let's call it a 0.5 volt from the sun, back down from the saturation point. And now we have a 56 dB signal to noise ratio. Okay, and you can actually see it here. It's significantly higher. Now, let's look at that signal to noise ratio, and I'm going to put too much bias on it, which means I'm now forcing the diode in well beyond the point where my bias equals the sunlight noise coming from the diode. And watch what happens to that signal to noise ratio. Okay, I'm going to increase it and then we'll walk over. Okay, and it's starting to drop off right now. It's down to 52. Here's a better way to look at it. We'll use the signal history function. Okay, and let me just speed it up a little bit here so we can see more results on the screen. We'll go to, let's try medium. Okay, so that's the signal level versus time, right? And let's take the bias off. Okay, we went from minus 70, excuse me, from minus whatever it was, 50 or so, roughly. Let me expand the screen out so it's easier to see. I have more steps per division. All right, so we're running at about minus 68, 69, okay? And you can see it changed a little, right? Because a cloud came over. It's not as bright out there. But I'm going to put the bias on now, and let's go back and look at it. You'll see a historical view of what happens. Whoops. Okay, there's where I messed up for a second there. Okay, now it's too much bias because we lost the peak. So I'm going to bring the peak back by rotating the bias control down till I got just enough to overcome what the sun is doing. Now I'm going to go all the way down to no bias again. Okay, and notice how the signal goes back into drops by significant amount. We're forcing that photodiode in and out of saturation. So I'm going to adjust it up. Okay, so there's some level of reverse bias on this diode. Pull it off. 67 to whatever it was, 54. It's like 13 or 14 dB of signal level to be gained. So again, just a very small 1.5 volt battery. Let me turn the light on for that. Sorry if this is kind of jumpy, but this is the only way that I could really do it. We have a 1.5 volt battery here. It's sitting across the pot. It's 100K. The diode connection before it hits the input capacitor to this amplifier is where I have a 100K resistor. And since that's a really high input impedance point, you want to have 100K, and you don't want any noise coming in on this lead, which is why this 0.22 is sitting there. Okay. Now you can look at this and you'll say, wow, propagation is changing, but not really. It's just the sun coming in and out from behind clouds, causing the receiver to go into saturation. And so I'm going to put the bias on again. Okay, so there's the compression. I have now forced that diode to be in its linear range again. So the question now is, hey, it looks like it works really good with big signals. Let me put the signal into the noise and I'll be right back. By the way, guys, I wanted to make mention of this as well. I've pointed this receiver off axis. So now that really large signal I had is very small, right? So here's a test. I want to show you this. Here is a extremely bright handheld flashlight, and I'm going to point that right into the lens. Excuse me, not in the lens, but right in front of the detector, and see if we go into compression. Okay, that's with that bright flashlight right in front of the lens. Well, what the heck is going on here? Why isn't that causing a problem? It causes a bit of a problem. Actually, that spot right there is where I covered up the detector. Anyway, the reason why this doesn't cause any problem is because we've already taken the precaution of filtering the front end of this detector with a 940 nanometer, very narrow bandpass filter. And LEDs themselves, unless they're designed for it, don't put out any IR information, any IR power. That's why I'm able to operate this in these lights, in front of this light, and again, almost no difference. Well, no difference. Okay, so now let's see. Now that we have this really weak signal, let's go back to signal history. Let's go back. Yeah, turn the signal history back on. Where is it? Down here somewhere? Oop. What am I doing? I don't know what the hell I'm doing. Oh, here it is. Get out of there. Okay. Let me just make this a little smaller. So you could see there's some, what it says, you're 20 dB above the noise floor. Now, again, don't look at that as actually 20 dB above the noise floor, because when I go over here to just the noise, it's 13 dB, 14 dB above the noise floor. So this works relatively between two levels, but it does not work very well as an absolute from the noise floor. All right. So one more time, there's our signal level. Okay. There's our receive level. And now I'm going to go apply bias. Son of a gun. The bias was already on. But I'm going to take the bias off. Okay. So I take that back. The bias is now off, and the signal is buried in the noise. Okay. There's really nothing detectable there. And you can see everything dropped off here as well. Let me make this a little smaller. Okay, let me go back. And now what I'm going to do is I'm going to put the bias back on. And I'm doing this all with clip leads, so it's easy on and easy off. Okay. There's the signal we're looking for. Okay. And I'm going to turn the bias up too far. Actually, I turned the bias down to its lowest point right now. Because we're in full sunlight, that's just not enough to bring the diode back into the conduction area where it's not saturated. So let's bring it up. We're going to turn the bias up. And there's a point at where, if you look at the bottom here, the signal is much stronger, right? Using the signal history mode. I'm going to see if I can get it to the point where it falls off again. Now I've got the bias all the way up. And you can see that the signal has dropped off some. Right now it's extremely sunny out there, so I need as much bias as this thing can provide. All right, so I guess any questions if you guys want to ask, or we can get together on a Zoom meeting, whatever. John, Renee, Glenn, Fred, myself, and talk about some of this. So I'm going to be... Guys, I just want to add one more thing here at the end. If you look outside, it's still overcast, but much brighter than it was just a couple of minutes ago. Let's take a look over here. Here's the signal amplitude over time. This is minus 53 or so. This is minus 50. This is because the sun amplitude is changing, and even with small amounts of light from the sun, the detector gets pushed into saturation. So as you can see, as it gets darker, the signal level starts being able to expand and comes out. So I just wanted to throw that in there. This is 350 seconds. This is about a 10-minute scan here across the screen. Again, I have to apologize for the handheld on everything here, but it was the only way I could really do this. So thanks for bearing with me. But this, I think, is going to be a game changer for daytime optical communications. Out 73 W1 VLF.